regression. And ideally, we would always have two vectors in 3D space that are intersecting at some point. So these come off the eyes. Your eyes, basically the tangent plane to your eye is always like a ray into space. And if we could find the intersection of those rays, we would always know where and at what depth you're looking. However, the eyes are relatively small. There's some error in the eye tracker. The human eyes are not perfect, so sometimes you get eyes that are a little bit cuckoo and not exactly intersecting. So we need some way to deal with this. And basically we take a series of data, training data, and we can calculate, so even if a vector is parallel, so for example, you're looking at a distant place in the environment and the eyes are near parallel, the eye tracker may see it as parallel, but using the support vector regression, we know that they're just looking at the farthest plane, or sort of far into the distance. So we get an approximate estimate of depth in this case. So even though it's approximate, and you'll see exactly how approximate it is in just a second, we still need a better, more robust way to calculate what plane somebody is looking at, and to do this for multiple users without calibration, for example. And to do that, we use a support vector machine. So basically, analyzing, taking a series of data, gaze into different planes, we can very accurately calculate what plane somebody is looking at, and whether they've moved from one plane to the next. So, first to test this, I mentioned we use a pilot experiment to determine what ideal distances would be, distances between focal planes would be. So what we did is we set out to just track the eye tracker on physical objects. So we put a sheet of paper with a plus in front of participants and moved it to different points in 3D space and tried to see what accuracy we could get with the eye tracker. And this would allow us to determine how many focal planes we could track and at what distances they would be, what the best distances would be. So I'll explain all these graphs. So another thing, during the pilot experiment, people would move their heads back and forth while looking at the plus, so we got data at different angles. So that's what this first graph in the upper right or upper left represents. So this is estimations, relative estimations as a user is turning their head between 15 and negative 15 degrees, so just back and forth. So the first on the very left, the blue dots represent 10 centimeters, and then the red is 30 centimeters, and so on and so forth. Up to about 1.5 meters, we can sort of get a good approximation. But after 1.5 meters, it becomes very difficult. So we really don't know where, if someone is looking at 2 meters, 5 meters, 10 meters. And this is actually just for a single user. But for all users, there are 4 users in this particular pilot experiment, we tried to get an exact estimate of where they're looking. And so you can see the ground truth here is on the bottom, so this is the actual number of centimeters, and on the left is the estimation from the device. So you can see, at first it's quite accurate, so for 50 centimeters, 150 centimeters, up to about 1 meter, we have pretty good estimations. But at 3 meters, even though the ground truth is 3 meters, we only get an estimate of 250 or so, and it gets worse as you go farther. So the goal is to choose the best focal plane separations which were the least likely to overlap. So the ones we picked are represented by the gray zones on the right. So the first 2 zones are relatively small because we have some degree of accuracy, and then anything over 2 meters is considered the last plane, and that's how we accurately select the gaze plane. Okay, so the second study was to see if people could actually use this for interaction. So when they're looking in the display, can they use it to select an icon, and if so, how well can they do it? So we set up an experiment based on the pilot experiment, so with those focal plane distances. And here you can see a simulated, on the right-hand side, there's a simulated view of what users saw, although the blue lines were not there. And these are essentially icons with different textures and different, so the first one is a texture where you can very clearly see the texture and there's no blur. The second one is slightly blurred and the texture is more fine-grained. And the last one is very blurred with almost no texture at all. So the idea was, using these depth cues, can we help people to, let's say, focus on a particular icon? Perhaps some blur or size would help people actually focus on something and help us improve accuracy when calculating the focal plane. And on the left-hand side, this is an actual view through the multifocal plane display. It doesn't give a good representation because it's a camera taking it, but it gives you some idea of what people saw during the experiment. Okay, so these are basically the results we got. So let me explain what you're seeing. On the left-hand side of this image here, this is sort of the ideal case. It's really what we want. The green dots represent individual gaze samples, so every 30 milliseconds we take a sample. And the blue, the green represents the first focal plane, the blue represents the second focal plane, and red represents the third focal plane. This was basically for the best user. So they had an average, so for this child they had a 98% plus accuracy. The second trial is, there was only one of them. It's sort of what we don't want, a very clustered, so perhaps that user's eye gaze data was, their eyes were closer together, not as robust, but we still got a good, fairly high accuracy in identifying a gaze plane. So there's still relatively good separations between the green. You can see there's some green up on top, which we didn't want, but the blue and red are still relatively well separated. And then on the right is a plot of an average user and all of their trials altogether, which for the most part, overall, we had about 98% plus accuracy for almost all users. So pretty good classification. One thing we did observe, there's no effect of depth cues. So we sort of expected maybe clear depth cues would be easier to track, would have less variance for the eye tracker, but that was not the case. So it's possible that depth cues cannot be used to improve gaze tracking accuracy in this type of display. And lastly, we were able to do this very quickly. So when a person switches from a gaze plane to a different gaze plane or to the environment, it's when within a couple frames, for almost every user within 100 milliseconds. And you'll see a demo video in just a second. So I have a video, which I'll show in just a second, and you'll see the user's eyes, so where the user is looking, as well as one of the icons used in the experiment. And you'll see as soon as they look off of the icon, there's some text at the top which tells you whether or not they're looking at the screen. Ideally, we'd like to take a video through the view of the display itself, but we can't do the eye tracking process with the camera in front of the user's eyes. So this is a simulated view, which you'll see. All right, so the red plus represents the user's eye gaze, and he's looking at the screen. As soon as he moves up, you see it's very quick. We can determine that he's moved off into, even though it's still occluded by the focal plane, we know that he's looking at the wall behind. So within within 100, maybe 200 milliseconds for almost all users, we know that they've moved off the display and they're looking at something in the environment rather than something on the display. So we can close text very quickly. Okay, so to conclude, we now know that stereoscopic depth tracking is possible, despite only having monoscopic depth cues. So despite only having a display like Google Glass, we can still do depth tracking to some extent, though it's not super robust. And then we also know that if we discretize this plane, so if we have a multifocal plane display, we can very accurately know which plane the user is looking at. And lastly, though slightly unexpectedly, depth cues did not help people improve their convergence or focusing on targets. So. Future directions, we want to get to working outdoors, so we want to develop a portable model that people can walk around outside and we can measure and test more usability for interaction. Also, intelligently managing the plane. So usually, for example, most single plane displays are fixed at like 1 meter, but a user's eyes are not always fixed at 1 meter. They're looking at different places in the environment. So how do we get text to be less likely to occlude environmental objects, for example? We would also like to build a smaller, lighter prototype, and we could potentially use this for surgery, for example, if someone needs to view patient data and then they look back into the surgery process and they don't want to see it anymore, as well as for the patient-doctor relationship. So thank you. Special thanks to DFKI and Osaka University's Humanware program for making this research possible, and I'd love to take any questions.